Hello, Alfred.
Hello, ma'am. Narinig po ako.
Oo, malinaw na. Wait. Ano kaya? Wait lang ha.
Okay po.
Malinaw. Pero, sine-check ko kung paano lalabas yung screen mo. Ayan, nakalabas na yung... Kasi dalawa yung monitors ko, yung isa sa sa YouTube. So yung isang screen tinitingnan ko yung YouTube live. May delay. Yay.
May delay ang YouTube. Inisip ko kasi ma'am ko kapag nandyan ako, mag-aagawan tayo ng bandwidth. Malinaw ba yung akin ngayon?
Malinaw.
Malinaw naman. Kasi baka mag-agawan tayo ng bandwidth pag nandyan din ako. Tapos bumagal na sobra yung sa YouTube.
Paano ba to? Ang weird. Parang time warp. Hindi, malaki naman ang bandwidth kasi optical fiber. Hindi naman. Malaki yung bandwidth ko dahil nga optical fiber. Di ba nga 40 megabits per second upload. So, mas less delikado pag dito. Isara ko kaya muna to para hindi ko nakikita. Kasi i-off ko to kasi naririnig mo, di ba? Naririnig mo?
Hindi naman, ayun po. Boses nyo lang narinig ko.
Oh. Close ko muna yung Mac Defense kasi mukhang okay na eh. Nag-work na yung Mac Defense. Yan. Okay. Okay. Sige. I think nag-work na yung kasi nakita ko na eh. Tapos, ang mangyayari, meron maliit na screen sa taas na nandun yung face mo. Kung naka-on yung video mo, kung hindi, okay lang. Pero nakikita na yung screen mo ngayon, yung slides mo. Okay. Sige. Shall we begin?
Sige po. So good afternoon, everyone. I am Alfred Piabella, and I will be presenting my dissertation with the title Eulerian Vorticity on and Beneath Surface Waves Generated at the Liquid Gas Interface. Here is an outline of my presentation. First, I will read the abstract, then a brief introduction discussing previous studies and the particular problems to be solved. Then I will discuss the linear water wave theory and analytical modeling, the spatiotemporal analysis of surface waves generating octopole vortices in a square domain, the Eulerian vorticity in octopole vortices generated by nonlinear surface waves, and the Eulerian vorticity beneath rotating surface waves. And finally, I will discuss the conclusions. So here is the abstract. In this dissertation, I show the existence of the Eulerian vorticity on and beneath surface waves generated at the liquid-gas interface. The first case involves a generation of octopole vortices by a square waveguide. The octopole vortices, characterized by orbits of gyrating particles, are produced by rotating waves. These rotating waves are a superposition of phase-shifted, oblique, and orthogonal progressive waves. I modeled the motion of the advected particles using a technique which utilizes the superposition of velocity potentials and the analogy of the Eulerian vorticity contribution with the usual Stokes drift contribution generated by the surface waves. For the second case, I show the existence of the Eulerian vorticity by investigating the motion of submerged particles in vortex lattices beneath the liquid-gas interface or in the liquid bulk. The results are in good agreement with the previous theory, which takes into account the additional Eulerian vorticity contribution. For the introduction, I will discuss the particle control via surface waves in previous studies, the statement of the problem, and the novelty of the study. In previous papers involving floater particle control via surface waves, the clustering of the particles based on their wettability have been studied, such as this paper by Lukashuk and co-workers. We see here in A that initially the particles are scattered on the air-water interface, while in B, they are clustered and trapped along the nodes of the standing capillary surface waves, as shown in C. In another paper entitled Microscale Assembly Directed by Liquid-Based Template by Chen and Company, they studied liquid-based templated assembly for tissue engineering purposes, and they were able to generate different patterns after vertically shaking small polygonal containers. The waves generated by the shaking of the container produced these static patterns of tissue cultures. Large-scale counter-rotating eddies have also been generated inside the laboratory with the use of linear and nonlinear waves by Ponsman and his Australian group. The waves were produced by cylindrical wave makers, which were half submerged on the air-water interface and oscillated vertically. The nonlinear waves are oscillons, which force the central jet of the vortex pair to travel towards the wave maker in somewhat of a tractor beam effect. Also, using cylindrical wave makers configured as shown in the experiment setup, the Russian group of Filatov was able to produce vortex lattices using orthogonal and phase-shifted surface waves. And they measured the corresponding vorticity at the air-water interface. Note that this was published in JETP Letters last 2016. The theoretical description of the phenomenon was discussed in their Physical Review Letters paper, Nonlinear Generation of Vorticity by Surface Waves, where they showed that the vertical vorticity, that is, the z component of the vorticity or the curl of the horizontal velocity field, to be this expression. A rebranding of this vortex lattice experiment was done by the same Australian group mentioned a while ago, now led by Francois. They named these vortices as wave-based liquid interface metamaterials and published their results in Nature Communications last 2017. They did not cite the experimental study of the Russian group and discussed how these vortices consisted of nested and gyrating particles, only visible using a high-speed and high-resolution video recording. They also added that these vortices are generated by rotating surface waves, since they knew a technique to image the surface waves with high spatial resolution at the liquid-gas interface, while the Russian group did not have a 3D wave imaging technique at that time. Another theoretical work by a part of the Russian group led by Parfenev improved the description of the vorticity and generalized it for depths lower than the interface. Notice that the spatial structure of the surface waves generating the eddy currents derived using their expression is similar to the ones obtained by the Australian group. Now, in the paper of Francois and company, wave-based liquid interface metamaterials, they mention the following. Note that the physics of the Lagrangian circular drift revealed here is intrinsically different from a recent Eulerian theory of vorticity generation on a surface perturbed by waves, which considers bulk viscosity as the essential ingredient of the mechanism. This recent Eulerian theory pertained to in the text is the paper I showed a while ago by Filatov and company, with the vertical vorticity given by this expression. In this reference, they missed the Stokes drift contribution, which therefore gives 2 plus square root of 2 for the vorticity prefactor at the interface instead of 1 plus square root of 2, which was corrected by Parfenev and company in their PRF 2018 paper. And notice that if I plug in the value z equals 0 in the prefactor, e raised to 2kz plus square root of 2 e raised to kz square root of 2, we get the value 1 plus square root of 2. However, in the experiments of the Russian team, they found that this prefactor can reach up to 14 instead of 1 plus square root of 2. Sources of error include friction with the boundaries and capillary forces on the interface. To state the problem further, in the paper of the Australian group, they computed the velocities of the particles using Euler equations with the implicit assumption, which means that the viscosity have been neglected. For now, just focus on the two terms that I will mention, namely the Stokes drift contribution and the Eulerian contribution. I will explain these two in more detail later. In their model, the linear wave velocity UP can be solved using the implicit assumption. And this already provides the Stokes drift velocity contribution, U sub d, generated by the waves. The waves cause the particles to undergo fast gyrations or the curling of the trajectories and a slow drifting while they propagate. Now, qualitatively, one can already recover the vortex lattice pattern shown here from this velocity contribution. What they observed was that the Stokes drift contribution from UP was not enough to describe quantitatively the velocity of the slow drifting that they measured in their experiments. So they added another U sub d, but they adjusted the magnitude to match their experiments. That is why they added alpha U sub d. So they used two contributions for the total velocity field, which is UP, which takes care of the fast gyrations and the Stokes drift velocity, which translates the particles, and another Stokes drift-like contribution to match their experiments. Meanwhile, the Russian team computed the period averaged vertical vorticity of the vortex lattice using the Navier-Stokes equation, considering now the viscosity of the liquid. The vertical vorticity is the z component of the curl of the velocity field. They also found two contributions to the vorticity. The first is the Stokes drift vorticity contribution, while the second is the Eulerian vorticity contribution owing to the viscosity of the liquid. I can now ask then the following questions. First, can this additional Stokes drift-like contribution detected by Francois and company also be detected for a different vortex structure other than a vortex lattice? And second, does this additional contribution correspond to the Eulerian vorticity contribution, which was missed after neglecting the liquid bulk viscosity? Now, how can these questions be addressed? For the first one, I generate a different vortex structure, particularly an octopole vortex, and compare it with how a vortex lattice is generated. I also model this vortex structure and show if an additional contribution indeed improves the experimental model agreement. For the second question, I will prove the prediction of Parfenev and his group by measuring the vorticity beneath the liquid gas interface for a vortex lattice. One novelty of the study is that the motion of octopole vortices inside square wave makers has never been studied before. The Australian and Russian teams have previously generated the vortex lattice. Now I have generated an octopole vortex and obtained closed form expressions for the velocity field and waves affecting the particles. Second, the vorticity beneath the rotating surface waves which generate the vortex lattices has never been examined before. That is, I will show experimentally that vorticity generation by surface waves requires the Eulerian contribution owing to the liquid viscosity. Now, I will be discussing the linear water wave theory and analytical modeling, including the governing equations and boundary conditions, the solutions to the boundary value problem, and the modeling of rotating surface waves and vortex lattices. A diagram for the boundary value problem specification for periodic water waves is shown here. We make use of the Laplace equation, where phi is the velocity potential and the velocity field u is del of phi. To simplify the analysis, we will consider for now a wave that propagates along the horizontal x-axis with heights measured along the vertical z-axis. The bottom boundary condition imposes zero flow through the rigid bottom. The kinematic free surface boundary condition relates changes in the surface displacement to the potential components of the flow. The dynamic free surface BC expresses momentum balance at the surface z equals eta, and the periodic lateral BC imposes wave periodicity in space and time. To solve the boundary value problem, we use separation of variables so that we can express the velocity potential phi of xz e as a product of terms, each of which is a function of only one of the independent variables, x, z, and t. From the periodic lateral boundary condition, we know that phi must be periodic in time, with capital T as the period of the wave, and we can specify the function cursive capital T of t as sine omega t. So we can write the potential in this form. Then applying the boundary condition, we get the following. And this equation is true for omega equals 2 pi over t, where omega is the wave angular frequency. Now, plugging in the current form of phi to the Laplace equation, we get this. And dividing this expression by phi, we get this equation. The only way that this equation would hold is if each term is equal to the same constant, except for a sign difference. And we can write the following. The constant k for this case has been chosen to be real and non-zero so that phi becomes periodic in x. Therefore, we have these expressions for capital X and Z. So that the potential velocity potential now becomes this. Now again, using the periodic lateral boundary condition, we can write the following, which is true when the constant k equals 2 pi over L, where k is the wave number and L is the wavelength. Now we can retain the first term inside the brackets of the potential above to get this. Note that this is still a solution to the Laplace equation due to the principle of superposition. Substituting phi to the bottom boundary condition, we get the following. We equate this to 0 and find that c must be d exponential 2kd. And then substituting the value of c back to phi, we get this. Simplifying further, we write phi equals g cosine kx cos kz plus d times sine omega t, where g is as shown. Next, we need to apply the dynamic free surface boundary condition, where g is the gravitational acceleration and z equals eta is the wave interface. This condition originates from the Bernoulli equation, which can be used to specify constant pressure on the liquid surface. The Bernoulli equation must be satisfied on z equals eta of x, t, or on the surface, which is initially unknown. So we have to evaluate this condition by expanding it about z equals 0, which is known to give us this equation. Moving on, we can linearize this expression by retaining terms in the order not lower than eta, and rewriting, we got an expression for the surface wave eta. From before, we got this expression for the velocity potential phi, and using this to the linearized expression for eta, we get the following. This suggests that eta can be written as constant times periodic terms in space and time plus a function of time. We can set the Bernoulli function c of t to be 0 if we define eta to have 0 spatial and temporal mean. From the diagram shown here, we can thus write eta equals L over 2 cosine kx cosine omega t. And comparing the two expressions for eta, we get the value of the constant g. Now plugging this value into the velocity potential, phi, we get this final solution to the Laplace equation, which is the velocity potential for a standing surface wave. And note that phi is now written in terms of the known quantities capital L, omega, k, and d. Now, given this expression for phi, we can also write another solution given by this expression. And this differs from the previous form of phi in that the x and t phase terms are shifted by pi over 2. Now, subtracting this to the original form, we get another solution. We can then again shift the overall phase by pi over 2 so that we get the velocity potential for a progressive surface wave propagating towards the positive x direction. We now proceed with the modeling of the rotating surface waves and vortex lattices that I showed a while ago. The experiment set up to produce the vortex lattice involves two wave makers, which produces waves that propagate along the x and y axis. This pair of waves should have a phase difference of pi over 2 to generate the vortex lattice. These wave makers are placed against the walls of the rectangular water tank, so that waves are also produced due to wall reflections. We already know the velocity potential for our progressive surface waves as derived a while ago. And now we can write the velocity potential for the superposition of orthogonal progressive surface waves with phase shift along the y-axis, coming from the wave makers and the walls, as this. And simplifying, we get this expression for the velocity potential producing the vortex lattice. We can then get the velocity field advecting the particles to form the vortex lattice, since UP is just the gradient of phi, and the phase shift psi equals pi over 2. The subscript P denotes the potential assumption for UP. The velocity field generating a vortex lattice is then given by this expression. And note that this is linear with respect to the trough to crest wave amplitude, capital letter L. Integrating this velocity field in time generates the vortex lattice. Shown here is an example of a 2x2 lattice from the paper of the Australian group. To generate an n by n cell lattice, we must set the wavelength lambda equal to 2s over n, where s is the side length of the square domain where the lattice is generated. We can then get k from lambda, And we can get the wave angular frequency by plugging in k to the dispersion relation for the surface waves, where omega equals 2 pi f, the surface tension is sigma, the density is rho, and the water depth is d. This is my own render of the particle trajectories for a 3 by 3 vortex lattice done in MATLAB, and a vortex cell on the right. We can clearly see that a vortex cell consists of nested and gyrating particles. They also drift from their initial positions, which are indicated by the black dots. To model the rotating surface waves, we use the recasted form of the dynamic free surface boundary condition to make use of the velocity field for the vortex lattice that we've derived a while ago. Substituting and simplifying to retain terms up to order eta, we have this expression for the surface waves with the following contributions. This is a visualization of the Australian team for the surface waves. They said that these waves are rotating since the wave crests and troughs change positions in contrast to standing waves. The rotation of the waves provides the momentum for the particles to drift within the vortex lattice cells. To visualize what happens during experiments, I made my own visualizations of the rotating waves in the vortex lattice. If we randomly place floating particles on the liquid surface, which trace the motion of the fluid particles, we will see something like this. Notice how the waves are rotating, but the motion of the tracks of the particles are not so obvious. To visualize the vortex lattice, we must keep track of the path of the particles shown here. Now we can see the gyrations and drifting of the particles as they are vectored by the rotating surface waves. Here is another visualization without the waves. You can clearly see the nested gyrating particles within each vortex cell. Now, if we look at this vortex cell, if we focus our attention to specific regions through which the fluid flows in time, then we are looking at an Eulerian view of the flow field, and we see closed orbits, such as this one. Next, if we follow the motion of a specific floating particle or fluid parcel in time, then we are looking at a Lagrangian view of the flow field, and we see something like this. In the Eulerian view of the flow, there is no mass transport, and the particles form closed orbits after one period. While in the Lagrangian view, there is mass transport, and the particles form open orbits after one period. This mass transport distance is called the Stokes drift. We can also obtain the Stokes drift velocity, u sub d, that is for a particular oscillating in the neighborhood of its original position. We can write its instantaneous velocity in terms of the velocity at its original position, x naught, where delta x is as given here. Now, getting the period average value of this velocity, we get the following equation. The term on the left of the equal sign is the average Lagrangian flow velocity, or the mass transport velocity. The first term on the right is the Eulerian velocity contribution, and the last term is the Stokes drift velocity contribution, u sub d, which causes the mass transport, or the Stokes drift. Now, if we use the previously obtained linear wave potential velocity field for the vortex lattice UP and substitute it to the equation for the mass transport velocity, we find that the Eulerian velocity contribution due to UP is 0, and only the Stokes drift from UP contributes to the overall transport of a particle from its initial position. Even though the Stokes drift from UP contributes to the overall transport of a particle, Francois and his co-workers noticed that this contribution was not enough to match the experiment results. So they had to add another Stokes drift-like contribution, but with the velocity magnitude adjusted. They calculated the Stokes drift velocity U sub d from UP to get this, and its amplitude is given by B. They adjusted B, but they did not describe the exact method and parameters they used to compare and adjust this quantity to match their experiment. Now, if I compare, or no, to summarize, in the paper of the Australian team, they modeled the velocity using Euler equations with the implicit assumption, so that there is an additional Stokes drift-like contribution to match the experiment, and a potential velocity which already includes the Stokes drift contribution from the linear wave motion. Now, if I compare these two equations, I believe that the additional Stokes drift-like contribution that they added to match the experiments correspond to the Eulerian vorticity contribution, but not due to the waves. In fact, based on the results of the Russian group, the period average vertical vorticity, considering the liquid bulk viscosity, involves a Stokes drift contribution and an Eulerian vorticity contribution owing to the liquid viscosity, which has the same horizontal structure as the Stokes drift. In my experiments, I will show that this additional contribution exists for an octopole vortex. Also, contrary to the statements of the Australian team regarding vorticity generation of their vortex lattices being different from the theory which takes into account the liquid viscosity, I will show experimentally that the Eulerian contribution owing to the viscosity is indeed necessary. Now, in this part, I will answer the questions, or the question, can the additional Stokes drift-like contribution also be detected for a different vortex structure other than a vortex lattice? And to answer this question, I generate a different vortex structure, specifically an octopole vortex, and compare it with how a vortex lattice is generated. In the paper of the group of Chen, I showed a while ago that they implemented liquid-based templated assembly for tissue engineering. Here is their setup. They place the cultures inside a 1 cm by 1 cm square cross-section vessel that is vertically shaken so the surface waves are produced. Now, observe that they have also produced similar vortex lattices, but particles cluster along the separatrices and do not gyrate and drift. That is, standing waves and not rotating waves produce these patterns. Another pattern that they produce is this. It has 8 separatrices shown through the green lines. And aside from horizontal and vertical lines, for the vortex lattice, diagonal lines are also present in this pattern, in contrast to the vortex lattice. The question is, can I get a similar pattern with 8 separatrices where the particles gyrate and drift instead of being clustered as shown? Since the particles gyrate and drift for the vortex lattice of the Australian and Russian teams. That is, there is mass transport. And then I ask another question. Can I model this pattern using the same technique described previously? To do this, I used a different setup to produce the waves. And here are the part specifications. A camera is placed above the entire setup. And an acrylic tank is filled with water up to some height. A subwoofer speaker is controlled using a function generator, and its diaphragm is attached to aluminum rod attachments towards a wave maker. The wave maker is an open square with edges made of acrylic cylinders. The wave maker is half submerged on the liquid gas interface so that as the speaker diaphragm vertically oscillates, it also oscillates, producing the surface waves inside its square domain. Tracer particles were used to track the motion of the liquid particles, and LEDs are placed below the tank for illumination. This is a video of the actual setup and operation, where this is the wave maker, a light diffuser for the LEDs, and here is the speaker. The resulting pattern of the trajectories of the particles using a frequency that produces an octopole vortex is this. This is a top view of the liquid gas interface inside the square wave maker domain. Notice that if we zoom in on the upper left vortex cells, we see that the particles gyrate while drifting, similar to that for the vortex lattice. Now, to generate this pattern, we measure the wave maker side length S, and then we compute the capillary length L sub C to consider the meniscus thickness, where sigma is the surface tension and rho is the density, and compute the effective vortex side length as L sub effective equals S minus 2 times the capillary length. The wave number is K equals N pi over L effective, where N equals 5. And we plug in the value of K to the dispersion relation using the following specifications for the liquid used, which is water. Omega is 2 pi F, so that we set the frequency generator to F equal to 7 Hertz for our case that produces the octopole vortex. So the answer for the previous question before is yes. And the particles drift. The particles drift towards the center of the wavemaker edge instead of moving away from it. Also, they move away from the corners. Now, is the drifting caused by rotating waves similar with the vortex lattice? To image the waves, I used the free surface synthetic styrene technique, or FSSS technique. Here is a similar setup shown before with a minor change. Here are the steps for the FSSS technique. The camera is placed above the setup as before. And now we place a random dot pattern below the tank. This is a top view of the interface inside the square wave maker domain, and we can see the random dot pattern. The pattern is printed on an A3 size paper with dots of 1 millimeter diameter each. Then we record videos with and without surface waves. A code should be implemented which corrects camera distortions and sorts the images. Using the PIV Lab software to compute for the deformation vectors, we can obtain the deformation displacement vectors, delta x, from the 2D PIV Lab vectors, v equals uv. We then get the surface height gradients from delta x, and then invert the gradients to get the surface waves. Here is the interface of PIV Lab. And here is an example of the two-dimensional PIV Lab vectors obtained from the deformation of the random dot pattern. Shown here are the green quivers are the vectors. This is the necessary relationship to get the surface height gradient along the x direction. And after integrating this, we can get the surface wave heights. The resulting wave heights using these vectors is this. Notice that the wave crests, or the highest portions of the waves, and troughs, or the lowest portions of the waves, move out towards the edges and move in from the corners towards the center. A different view of the waves is shown here. Figure A shows the waves at one video frame with half the wavelength as scale. Figure B shows the average temporal spectrum of the waves. The inset is a result of using a filtering technique which only shows the value of the average temporal spectrum around the forcing frequency f, which is f equals 7 Hz for all space. With this, we see that the wave nodes correspond to eyes of the octupole vortex. In C, the wave crest is tracked from the corner to the edge for one wave period t, and D shows the track of such wave crest in C as directed by the arrows and the black dashed line. It also shows the visited sites of the crests in red dots and the troughs in blue dots. From all these observations, we can say that the waves are also rotating, and this gives the necessary momentum so that the particles move in towards the edges and move out from the corners, forming the octupole vortex cells. Now, I want to know what wave components make up these rotating waves. So I want to isolate them based on their directionality. To do that, first, we get a line scan profile across X and stack with the profiles from other times, as shown here in A. Next, we get the two-dimensional Fourier transform, as shown in B, and obtain only the right and left moving waves by covering the second and fourth quadrants and the first and third quadrants, respectively, as shown here in D. To reconstruct the 2D waves at a specific time, we get the inverse 2D Fourier transform as shown in C, and repeat the entire process for all line scan profiles across X. The resulting restacked profiles after inverse Fourier transformation are shown in E for the right moving waves and in F for the left moving waves. A similar process can be done to get the upward and downward moving waves. Just stack the y-axis profiles instead. Notice that the right and left moving waves have components coming from the corners. To show these component waves, the same process can be done to both left, right, and upward downward propagating waves, but stacking line scan profiles across the y-axis and x-axis respectively. And these are the resulting component waves. Oblique waves is seen to be coming from the corners. So far, the results suggest that the octupole vortex consists of gyrating and drifting particles, similar to that observed in the vortex lattice. These two vortex patterns are both generated by rotating surface waves. For the vortex lattice, the rotating waves are generated due to the superposition of right, left, and upward downward waves, but have a phase difference between them of pi/2. Purely right, left, and upward downward progressive edge waves and oblique waves from the corners exist. On the other hand, to generate the rotating waves for the octupole vortex. But now, what is the phase relationship between these edge and oblique waves that generate the octupole vortex? To find out the phase relationship between the oblique and edge waves, I constructed a modified setup wherein only one edge of the square wave maker is oscillating. And then the diffusing light imaging DLI technique is used to image the waves, which uses milk water solution as liquid, and calibration is done to relate the wave heights to camera detected light intensity from the LEDs. For time t, these are the waves produced by the single oscillating edge. But at a later time t plus 1/4 of the wave period, or equivalently a phase delay of pi over 2, the straight edge waves are modified to this pattern shown in B. If I do the same wave isolation component technique described a while ago for these waves, we see that oblique waves exist after a phase delay of pi over 2 with respect to the edge waves shown in A. Now, if I rotate the instantaneous wave heights by 90 degrees, 180 degrees, and 270 degrees, and add this to the original wave heights, then we get this pattern for the superposition of waves from the single edge wave maker, which is very similar to the pattern shown a while ago when the entire square wave maker was oscillating. Now that I know the component waves, I can now model the rotating waves in the octopole vortex. The velocity potential for a progressive surface wave is given by this expression. Therefore, for the edge waves, I set a similar form for the potential phi sub E. The four edge waves come from the left, right, up, and down sides of the square wave maker, and we just replace x with y for the up and down edge waves. For the oblique waves coming from the corners, we write the potential phi sub O as given, where the phase shift small phi equals pi over 2 and theta, which indicates the rotation about the x-axis to be plus minus 45 degrees. Then the total velocity potential after adding up all 8 components is given by this expression, where the variables are as indicated. This closed form expression looks manageable, and since the velocity field UP equals the gradient of the velocity potential, I can get the following expression for UP. A while ago, I mentioned that an additional Eulerian contribution owing to the liquid viscosity probably exists, which should be added to the mass transport velocity. If I let this have the same horizontal structure as the Stokes drift U sub d, then I have to solve for U sub d given by this expression. And I get the following x and y components for U sub d, where these are the corresponding variables. The result of integrating the total velocity u with alpha equals 1 using a fourth order Runge-Kutta integration scheme is shown here. The octopole vortex can be observed, and zooming in on a portion shows the gyrations, while the particles drift from their initial positions, shown as the small black dots. Here we see an animation showing the tracks of the particles coming from or forming the octopole structure. A zoom in of the upper left portion of the square domain is shown here, and a 3D render of the tracks close to the eye of a vortex cell is also shown here. To model the surface waves, we again make use of the dynamic free surface boundary condition using UP and linearization to obtain a closed form expression of the wave height eta. And here are the waves at one time step in A, and in B are the visited sites of the crests and troughs. Notice that the pattern is very similar to the one we got before for the superposition of waves from a single wave maker. Here is a 3D render of the surface waves. The waves indeed move towards the edges and out from the corners of the square wave maker. Here's another visualization showing the particle tracks with the waves. With these results, I have shown that I can model the octopole vortex and the rotating surface waves which generate them. Now in this next section, we look at the second answer to the first question. Can the additional Stokes-Drift like contribution also be detected for different vortex structure other than a vortex lattice? For now, I model the octopole vortex structure and show if an additional contribution indeed improves the experiment to model agreement. That is, I will optimize the value of alpha such that U equals alpha UD plus UP. I modified the experiment setup for this part. So I want to measure the motion of the waves and the tracer particles, but I cannot measure these two simultaneously. C and D shows the random dot pattern with and without the waves for the FSSS technique. I used polyamide spherical particles with density and which closely matches that of water, which is the liquid used here. And a black cardboard is placed below to cover the dot pattern and make the white particles visible when the particles need to be detected. I also use corner LED illumination to increase the contrast. The measured waves for a time step is shown in A. B and C shows the wave heights in time, which gives the highest eta for the corresponding forcing amplitudes, which produce these waves. Now, increasing the forcing amplitude increases the wave nonlinearity. Crest to trough asymmetry can also be observed, which is characteristic of nonlinear wave. Due to this asymmetry of the crest to trough height and the difference in peak heights, describing the wave in terms of the mean wave steepness would not be ideal. Instead, I quantify the nonlinearity through this quantity beta equals 1 minus a tilde sub f over a tilde sub t. With a tilde sub f as this integral, which is the same filtering integral I've used before around the forcing frequency f, while a tilde sub t is the integral over the entire average temporal spectrum. I used 4 forcing amplitudes with the corresponding values of beta, and here are the sample average temporal spectra from which the beta values are computed from. Beta increases as the wave nonlinearity increases, and the contribution of the forcing frequency to the overall spectrum decreases. The non-dimensional wave steepness k eta is 0.12 greater than 0.1 for the lowest beta, and k eta equals 0.1 is the typical threshold for linear waves. Using PIV lab, I measure the horizontal velocities, u, of the tracer particles placed on the air-water interface after measuring the waves. The vertical vorticity is then computed as the curl of u. Here are the results for the average velocities in favor plots and average vorticities in color map for the 4 beta values. The vorticity amplitude increases from 0.7 to 2 for the highest beta. The vorticities weaken near the walls due to friction, so I zero padded these regions for each. I then proceed by optimizing alpha for the analytical model. Velocity u equals alpha ud plus up, where I ran alpha from 0 to 100 in steps of 0.1. I then compare the analytical vorticities with the experiment by separately minimizing two quantities. First, I minimize the peak of the distribution of the difference between the experiment and the model vorticities. To do this, first, compute the two-dimensional vorticity difference, delta omega, get the absolute value. Then we obtain the distribution of the 2D vorticity difference, d of this quantity. And lastly, we plot alpha versus the distribution peak. The other quantity is this, which is the spatial average of the 2D vorticity difference. Shown here are in the figures are plots of these two quantities versus the velocity prefactor alpha. We see that for all levels of nonlinearity beta, particular values of alpha do exist, which minimize these two quantities. And we denote these optimal values as alpha naught. Here are the example modeling results using the corresponding optimal prefactor values for beta equals 0.378 and beta equals 0.396. For alpha equals 0, meaning no Eulerian contribution, the peak omega reaches to only about 0.5 for beta equals 0.396, while it reaches 1.2 to 1.3 with the Eulerian contribution, which is much closer to the experiment peak omega in the order 2. Also, for alpha equals 0, vorticity holes are visible with smaller vortices close to the center. For non-zero alpha, the holes and smaller vortices become less evident in comparison to the larger vortices, which follow the experiments. Here is a more comprehensive plot of the wave nonlinearity level beta versus the optimal velocity prefactor alpha naught. The optimal value alpha naught decreases as the level of nonlinearity beta increases based on the plots. The scaling parameter alpha naught remains to be greater than 1. And for the case of vortex lattices, the factor alpha, which rescales the Eulerian contribution according to the analytical prediction of Parfenev and company, is alpha naught equals square root of 2, or about 1.4, at the interface z equals 0. Note that this value is very close to the factors obtained here for the octuple vortices for the highest wave nonlinearity level beta equals 0.396. The values for the no-pad cases are alpha naught equals 1.4, 1.5 using the two methods, while alpha naught equals 1.7, 1.8 for the padded vorticity cases. Thus, the modeling requires the existence of the Eulerian contribution alpha times UD to qualitatively describe the octupole vortices. For this last part, I will answer the following question. Does the additional contribution correspond to the Eulerian contribution, which was missed after neglecting the liquid bulk viscosity? The answer is to prove the prediction of Parfenev and company by measuring the vorticity beneath the liquid-gas interface for a vortex lattice. Let me recall the analytical prediction of the Russian group regarding vorticity generation by the surface waves. They found that for the vortex lattice, two vorticity contributions are present, namely the Stokes-Tift and Eulerian vorticity contribution. Now, how are these two contributions generated? As explained a while ago, the Stokes-Tift contribution is determined solely by the potential wave flow. Implicit assumption, so that's UP. The Eulerian contribution is 0, assuming potential flow. The viscosity of the fluid is what generates the Eulerian contribution, according to Parfenev and company. It violates the potential approximation in the description of the surface waves and leads to the appearance of a non-zero horizontal vorticity concentrated in a thin viscous sublayer near the interface. Next, this horizontal vorticity is tilted due to the surface wave crests and troughs, and thus contributes to the vertical vorticity observed in vortex lattices. Finally, this Eulerian contribution spreads to the bulk through viscous diffusion. What I did was generate the vortex lattice and attempt to show experimentally that this Eulerian contribution, owing to the liquid viscosity, indeed exists, but below the surface waves. The Russian group have already done experiments at the liquid gas interface and have shown that the prefactor 1 plus square root of 2 reaches much larger values due to contamination on the interface, capillary effects between particles, and wall friction. Now, shown here is my experiment setup to generate the vortex lattice. A camera is placed above. An acrylic tank with the indicated dimensions is filled with the liquid. The shakers are two woofer speakers controlled by a function generator. Light sources are bottom LEDs for the imaging of the waves, corner LEDs for the vortices at the interface, and a 532 nanometer diode laser for the vortices below the interface. The wave makers are half submerged acrylic cylinders with diameter of 10 millimeters, and I use two pairs. One pair with lengths L equals 100 and L equals 110 millimeters. Now, two types of tracer particles were used. Polyamide spherical particles for interface measurements, and slightly more dense but smaller silver-coated hollow glass spheres for below the interface measurements. Lastly, the liquid is 40% by volume glycerol water solution with depth equal to 20 millimeters and has the following properties. Rho is the liquid density, sigma is the surface tension, nu is the kinematic viscosity, and n is the index of refraction necessary for the FSSS technique. To measure the waves, only the dot pattern is placed below the tank and the bottom LED is on. To generate an n by n cell vortex lattice, we must set lambda equals 2L effective over n, where L effective is given by this expression, and this is the capillary length L sub C. For L equals 100 millimeters, we use F equals 5 hertz, and L equals 110 millimeters, we use F equals 4.6 hertz. Now, one wave maker for each pair is delayed by pi over 2 phase during the experiments. The result of the surface wave 3D visualization using FSSS is shown here. Notice that this is very similar to the movement of the waves compared to the Australian team's results. Thus, rotating waves are indeed generated by orthogonal and phase-shifted standing waves. Now, the question is, do these rotating waves generate the vortex lattice as expected? Shown here is a zoomed-in view of the liquid-gas interface. I use PSP or polyamide spherical particles as tracers, and the blue box is the region of interest for particle image velocimetry using PIV lab. Shown below is the interface for PIV lab. This is how the tracer particles move. We see that the vortex lattice is not readily visible. But if we stack the image frames every time step, this is what we see. The video frames were stacked to visualize the trajectories as shown in the video and in the image shown below. Now from this, I can say that rotating waves indeed do generate the vortex lattice. Using PIV lab, I again conduct particle image velocimetry using an interrogation window size of 64 by 64 pixels. And the resulting instantaneous velocity vectors are as shown. Now, to be able to say that the vortices I am producing is exactly similar with what the Australian group was able to produce, I checked whether the particles also gyrate while drifting. Using the instantaneous velocities of the center vortex cell, I employed a step-by-step integration scheme using the fourth order Runge-Kutta integration scheme to get finer steps in space. I interpolated the velocity values at the current location after the previous time step before proceeding with the integration. And this is the resulting image for 23 wave periods T. The inset shows us that the particles indeed gyrate while drifting inside the cells of a vortex lattice cell. With all these results, I can say that I have produced rotating surface waves and the vortex lattice at the liquid-gas interface. Now I'll describe the imaging of the vortices in the liquid bulk, far below the liquid-gas interface. Here is a side view of the experiment setup showing the wavemaker pair and the suspended silver-coated hollow glass spheres. In this image, the tank filled with the liquid solution is shown, and the direction of the laser sheet illumination for the particle image velocimetry is indicated by the green arrow. This is an enhanced version of the same image to show the mount connected to the wavemaker and the speaker. These parts were shown before in this part of the setup schematic diagram. The side view of the experiment operation is shown here. Notice how the waves are induced due to the vertical motion of the wave makers, and the laser sheet beam illuminates the desired liquid layer. Here is a top view of the center vortex cell for wave maker length L equals 100 millimeters for the depth Z equals 3 millimeters. And here is for Z equals 7 millimeters. The measured velocities were also used to reconstruct the particle trajectories, as shown here. Shown in H are sample radial profiles of the average velocity magnitudes for depths 3, 7, and 13 millimeters below the interface. This means that the velocity increases from the eye of the vortex cell up to the separatrix. Note that this is consistent with the observations of the Australian team. Now, to confirm the predictions of Parfeniev et al., which is given by this expression, the mean vorticities are computed from the PIV velocities using this expression. Omega equals the curl of the velocity field. And doing that, we get here the vorticity for Z equals 3 millimeters and Z equals 5 millimeters for L equals 100 millimeters for the center vortex cell. Now, to eliminate the dependence on lambda of x and y, since I cannot measure the waves simultaneously with the PAV, and I wanted to focus on the non-dimensional scaling p-factor, a reference two-dimensional mean vorticity omega reference, average over a fixed period, is set, which is closest to the interface. The vorticities at other liquid depths Z are denoted as omega Z. And then I computed omega reference over omega Z, which is a two-dimensional image, and got the distribution of this ratio. For L equals 100 millimeters, omega reference was measured at Z equals 3 millimeters. And here are the normalized density curves for the vorticity ratio distributions for the indicated depths. I obtained the peak of the distribution and the width at half prominence, or the maximum height. After which, I then computed the analytical omega ref over omega Z values using this equation and compare the results to the peaks of the distributions. Now recall that the first term is the Stokes drift contribution, and the second term is the Eulerian contribution owing to the liquid viscosity. Here are the results for L equals 100 millimeters and L equals 110 millimeters. The black dots are the averages of the density curve peaks using 3 fixed durations for every Z. For L equals 100 millimeters, the data span 27 periods from 195, 205, and 215 of the wave period. For L equals 110 millimeters, the fixed durations are as indicated. The lower error bars are the standard deviations of the peaks, and the upper error bars indicate half of the peak width of the distribution for the following durations. The characteristic time of vorticity evolution is 1 over 2 nu k squared, where nu is the kinematic viscosity and k is the wave number. And this time is 13t and 16t for L equals 100 and 110 millimeters respectively. The vorticity ratio distribution peaks are closer and lean towards the analytical values with the Eulerian vorticity contribution as shown in the plots. This suggests that the vorticity decays much slowly with depth than when the Eulerian contribution is neglected. Obtaining the distribution of the vorticity ratios instead of just computing the average value over all space is more appropriate, since this does not assume self-similar scaling of the ratios throughout all the pixels, since the shapes of the density curves differ from each other. Now, to further quantify the closeness of the experiment density curve peaks with the analytical values, I computed the percentile rank deviations. The percentile rank P gives the percentage of the number of data points over all the data that has a value that is less than or equal to a desired data value. Thus, it gives an idea of the location of that number on the distribution. I then denote the percentile rank of the analytical vorticity ratio with the Eulerian contribution with respect to the data as P sub E, while P sub N for the analytical vorticity ratio without the Eulerian contribution. Then delta PE equals absolute value P minus P sub E, and delta P sub N equals P minus absolute value of P minus P sub N, or the corresponding percentile rank deviations. A lower percentile rank deviation suggests that the density curve peak value is close to the analytical value. Here are the resulting percentile rank deviations for L equals 100 millimeters and L equals 110 millimeters. We see that for all samples, delta PE is less than delta PN. This suggests that the vorticity ratio peaks are closer and lean towards the analytical values with the Eulerian contribution. The Eulerian contribution, owing to the liquid viscosity, is indeed necessary to quantitatively describe the generation of vortex lattices by surface waves. Now, to conclude, in this dissertation, I have addressed the following questions. Can the additional Stokes drift-like contribution also be detected for a different vortex structure other than a vortex lattice? To answer this question, I have characterized a different vortex structure, which is the octopole vortex, and it is generated by rotating waves, surface waves, which is a superposition of phase-shifted oblique and edge waves. I also modeled this vortex structure and showed that an additional contribution indeed improves experimental model agreement. Now, the second question was, does this additional contribution correspond to the Eulerian vorticity contribution, which was missed after neglecting the liquid viscosity? The answer is yes, and I have shown that this additional contribution closely corresponds to the Eulerian vorticity contribution as predicted by Parfenev and company, by measuring the vorticity beneath the liquid-gas interface for a vortex lattice. Here are my relevant contributions. To my knowledge, there have been no studies before which show that rotating waves can also be generated by pi over 2 phase-shifted waves which are not completely orthogonal with respect to each other. And oblique waves were necessary to generate the diagonal separatrices for the octopole vortex and force the waves to propagate away from the corners and towards the edges of the wave maker. I suggest that a similar modeling may be applied whenever pairs of counter-rotating vortices appear on every edge of an arbitrarily shaped domain. For example, in the small-scale polygonal wave tanks presented in the paper of Chen. Now, in obtaining the non-dimensional factor alpha, which rescales the Eulerian contribution for the octopole vortices, I described two methods. The first method obtains alpha naught, which gives the minimum peak in the normalized kernel density curves of the vorticity difference distribution. The second method obtains alpha naught, which yields the minimum value of the average, spatial average vorticity difference. In the paper of Francois, they did not describe exactly how they adjusted the velocity field magnitude to match their experiment results. Here, I have clearly outlined the two methods that I used. Now, since the obtained alpha naught for all cases of the octopole vortex were greater than 0, the Eulerian contribution indeed exists and is necessary to qualitatively describe the phenomenon. Also, since alpha naught for all cases were greater than 1, the Eulerian vorticity contribution at the interface always remains to be greater than the Stokes drift vorticity contribution, consistent with the prediction of Parfenev and company for the vortex lattices, where the p-factor is 1 plus square root of 2, so that the Eulerian contribution dominates the Stokes drift contribution. I am also the first one to show the vorticity in the liquid bulk for the vortex lattice. In previous studies, the Eulerian vorticity contribution at the interface had discrepancies caused by capillary and wall boundary effects. These factors were attempted to be corrected by Parfenev by considering the existence of a thin film at the interface. Here, in this dissertation, I have eliminated capillary and wall boundary effects by looking at the vorticity in the liquid bulk and at the center vortex cell of the 3x3 vortex lattice. The peak widths of the density curves of the vorticity ratio distributions encompass the analytical value without the Eulerian contribution. But the peaks and the percentile rank deviations themselves suggest that although this is the case, the vorticity leans towards the analytical value with the additional Eulerian contribution. This shows that the Eulerian contribution indeed exists. I had lengthy discussions with Vladimir Parfenev himself, and we had the same thoughts about the additional Stokes drift-like contribution that the team of Nicolas Francois added to improve modern experiment agreement, being the Eulerian contribution arising from the liquid bulk viscosity. My results also suggest a spiral pattern due to the absence of self-similar scaling of the vorticity ratio distributions for the center vortex cell, which provides additional insights for future analytical investigations. My experimental study opens the possibility of manipulating particles beneath the liquid-gas interface and demonstrates how subsurface vortices can be studied further. I would like to thank my advisor, Dr. Maricor Ansoriano, my readers, Dr. Jose Perico Esguerra and Dr. Michael Francis Ian Vega II, and my examiners, Dr. Percival Almoro and Dr. Cesar Villanueva. I would also like to thank Vladimir Parfenev for the theory, and Dr. Sergey Filatov, Dr. Paul Fontana, and Dr. Huasha. I would also like to thank ASTH RDP Graduate Scholarship Program for my PhD. And here are the main references for this presentation. Thank you.
3:17 minus 2 minutes, 3 hours, 1 hour and 15 minutes.
2 hours.
2 o'clock tayo nagsimula eh. 2 o'clock.
1 hour pala, 1 hour.
So 1 hour 15. So 2:02 actually tayo nagsimula. Tapos exactly natapos ka ng 3:17. So 1 hour and 15 minutes, Alfred. Okay, tingnan ko lang muna yung YouTube video. By the way, nice slides, very clear. In fairness, nag-extend din si Reggie, tumagal din siya. Pero kasi may mga nagtanong in between. So may nag-clarification. Pero actually, even with that, mahaba pa rin yung presentation niya. Wait, tignan lang natin yung YouTube presentation. Okay. All right. Started streaming.
May cuts ba, ma'am, sa boses ko?
Wala.
Wala naman.
Wala. May konting ganon. So, maybe here. Ano ko kaya? Teka, itapusin ko muna yun. Do you hear that?
Alin, ma'am?
Naririnig mo yung... may naririnig ka?
Wala naman, ma'am.
Okay. So hindi mo naririnig yung inopen ko na ano na streaming.
Wala naman.
Wait lang ha. Kailangan ko lang i-stop yung live streaming. Wait lang.
Hindi po.
Sandali binabasa ko yun ano may instructions dito how to do it. Stopping the live stream. Ending the live stream. If you're streaming to YouTube, you can end the stream from YouTube. If you okay from YouTube, click the end stream and continue to the next section. Okay, sandali. So una muna sa YouTube i-end ko. Wait lang ha. Nice slides though. Okay, and okay, how do I end this? End stream. Okay, get end stream. Are you sure you want to end it? Yes, end.